So I'm going to talk to you guys about the Elm functional programming language. It's typed functional programming for the web. So Elm is a language that is kind of looking to compete with JavaScript. It's a language that compiles down to JavaScript, HTML, and CSS. And it's looking to be kind of the next big language for the web. The goal of the Elm language is to bring approachability to functional languages and bring maintainability to JavaScript applications. So why would you choose Elm? There are plenty of other languages that compile down to JavaScript. You've got Dart, TypeScript if you like types, and object-oriented programming. And then just things like Babel that already exist that compile down to JavaScript. So why would you go with Elm? One reason is purity. So every function in Elm is a pure function, which means it operates on inputs and it returns outputs, and it will always return the same value for the same input, right? So if you say add 3 and 3, you're always going to get 6. You're not suddenly going to get 6 plus somebody launched the missiles, right? There are no side effects in Elm, which sounds kind of boring. Like, how do you actually do anything? So the side effects in Elm are actually encoded into the type system. We have the notion of tasks, which are things that you want to do, like HTTP requests, and the notion of signals, which are inputs from the user. And all of that is encoded in the type system. So you have to specifically say or explicitly say that your function is expecting inputs from the world or doing some sort of side effect. So when you're looking at your program, you can immediately see which ones are interfering with, which ones are potentially impure and which ones are completely pure. Immutability, there's all data in Elm is immutable. So anytime you have a list and you want to add an item to the list or take an item off a list, you're getting a new list back every single time. You can't, for example, here you can't do x equals x plus 1. That just doesn't exist, right? So this makes code easier to reason about. You don't have to worry about someone coming in underneath you and changing your values on you. Your data is always the same. Hey, that's better. It's designed specifically for front-end developers. The goal of Elm is to bring functional programming to the front end, right? Rather than bringing functional programmers to do front-end development, right? So it's designed specifically with front-end devs in mind, and it kind of sidesteps some of the scarier concepts from functional programming languages like Haskell. So if you've ever heard the term monad or anything like that, you're not going to see those in Elm. You'll see the patterns that monads kind of abstract over, but you won't actually see that there. There are some more complex ideas in Elm, such as signals, but there are libraries that kind of abstract over that so that you don't need to worry about it. But the machinery is still there. You can get under the hood if you need to. But the idea is be simple to get up and running and not scary. The tooling for Elm is awesome. So when you install Elm, it comes with an REPL, right? So you just hit your command line. You can interact with Elm. Elm Make is the build system. It's a pretty standard build system, to be honest. The package manager is really cool. The package manager is in charge of installing your dependencies, keeping things updated, and anytime you want to bundle anything up. What's really nice about it is when you go to bundle up your package, if you've made a breaking API change, it will tell you that you need to bump the version. It enforces semantic versioning for you. So you change the API, it says, sorry, you can't do this because you're not trying to bump the version number. You need to do that. It also allows you to diff packages so you can see any code updates, like whenever you update a package. And then you've got Elm Reactor, which is kind of the big ticket, like the wow item in there, which is, it's a process that you run in an Elm project, and then you go and you hit localhost, and it allows you to see all the Elm files in that project, click on one, and then see what it actually spits out into the browser. It's just a raw Elm file output, so it doesn't include any styles if you embed it into HTML or anything like that. But it does come with automatic recompilation, hot swapping of code, and a time-traveling debugger, which is like the huge wow factor for everybody. If you've ever seen Brent Victor's talk, Inventing on Principle, The idea is you run your code, and as it's running, you can pause it at any point in time. You can rewind, replay, and you can even go in and, while it's paused, change your code, have it hot swapped in, and replay those events using your new code. So very cool. There's great examples on the Elm site, one with Mario in particular, which is great. You can change the gravity on him. So now that I've totally sold you on Elm, right? So the Elm syntax, Elm is inspired by Haskell. It's actually written in Haskell and has similar syntax to both Haskell or ML. It's a little strange if you've not seen it before, so we're going to just run through some stuff. A lot of stuff is the same, literals are the same, operators are all the same, but some things are different. So functions, the top line there is a function declaration. So you're saying the name of the function, the arguments it takes, the equal sign, and then the body of the function. So add takes an x and a y, and then it adds the two together. To apply a function, you just, the name of the function, the two arguments, and then you get out your result. Now, bottom line is as a name, obviously, and then you've got an anonymous function. So the anonymous function begins with that slash, the x, the y, again, your arguments, and then the right arrow, and that's your body, and that's an anonymous function in Elm. Functions come with pattern matching. So if you like switch statements in other languages, it's basically the same thing as that. So here we've got a function or that takes in two booleans, and we're matching on the first. So if the first boolean is true, then we're going to return true. And if it's false, then we're going to return whatever the second boolean is. Functions also have special syntax called let, which basically allows you to create locally scoped functions and variables. So in this case, we've got some function that does whatever, but the idea here is double is a variable that only exists in this function, and we use it in that bottom line, double plus double. Lists are a very common data structure in Elm and lots of other functional programming languages. So list literals look just like array literals in JavaScript, and probably other languages, I don't know. Couple things with lists is you can, the double colon operator is called the cons operator. Basically takes an element and adds it to the front of your list. You can pattern match on lists, just like you can pattern match on other values. So the bottom example shows pattern matching on the x, cons xs. What that means is an element, one element in a list followed by some other number of elements in a list, okay? And what we're doing is we're plucking the first value off and we're returning that. The bottom one matches an empty list, and we can't take the head of an empty list, so we return nothing. And the just and the nothing there is from a special data type in Elm, which we'll see in a minute. Tuples, they're like lists, tuples, tuples, I don't know. Anyway, similar to lists, except they are of a fixed size and they can hold values of different types. So the first tuple there holds a number and a string. The second one, you can see. You can't add anything to them, anything like that. Once you have a tuple like that, that's it. Union types, this is where it starts to get interesting. So the top section there is a type that I've created called action. And action is a union. It is either an add or a sub or subtract. That pipe symbol there kind of separates the two possible values of the action type. And then we can use those types in a pattern match to say, okay, if it's add, add the two variables, and if it's, or the two arguments, and if it's subtract the two arguments. And then we can use it down here. We say calculate, add 1 and 2, calculate sub 3 and 5. So one other thing I forgot to mention. So if you are familiar with enums in other languages, C#, Java, it's very similar to that, only they're more powerful. For example, they can hold additional values. So the first type there is just an example of a union type like we saw before. The second one is still a union type, but it's only got one possible constructor. It's a counter. And it's a counter that holds an integer value, okay? So the step function that we've got down there takes some action, either increment or decrement, and a counter that's holding on to some value n. And if it's increment, then we're going to return a new counter with whatever the value was plus 1. And if it's decrement, we're going to do the same thing but minus 1. So we can say step, increment, counter 1, which means I get a counter of 2. Or I can decrement counter 2 and get a counter of 1. Going back real quick, when types hold values like this, it's not limited to a single value. They can hold multiple values. They can also hold, they can also be defined polymorphically. So you can say that you have, here's a type maybe, and it's a maybe A, when the A represents a type variable. It's some placeholder for some other type that you'll define later on. So we saw this earlier in the head example. Maybe is a type that has just A, just some value, or nothing. So it's used in a place of failure as opposed to using null. So you can say, okay, I have nothing, do this. I have just a something, do this. Another example of a polymorphic union is an either type, where you have two possible values, a left that holds value A, or a right that holds value B. This is also used in failure and success cases. Conventionally, the left side is where it holds onto like an error, and the right side holds onto your actual value if it was a success. Okay, something a little more familiar. Records look a lot like objects in JavaScript. So we can define a record. We can say a person is Jane Smith. The difference here being rather than colons, we're using equal signs to do assignment. Their records are very similar to tuples as well, except that you get named keys to actually access your data. And you get them as functions. So person.first is actually a function. What's interesting about the accessor functions is they are not tied specifically to that record, right? They operate on that type, but you can use it, you can say .last and send it a person. So .last is an actual function that will operate on a person. You can then, which means you can use that in something like a map or a filter or something like that. So here we say list.map, pull the last name off of, let's say we have a list of people somewhere. We can pattern match on it. So that function definition there, the say hi, what that says basically is say hi to any object that has a first name. Doesn't matter, or any record that has a first name. Doesn't matter if it's a person, dog, it doesn't matter. As long as it has a first name, it's fine. This is called row polymorphism, or structural typing, or static duck typing is another name for it. So anything that has a first name, we can say hi to that thing. Records can be updated. Again, everything's immutable, so anything that you do to a record returns a new record. The original record is just basically used as like a template, kind of. So the first example, person minus first, removes the first. The second example, the pipe and age equals 20 adds a new field age to that person record, giving you a new person record. The third one, again, we're using the pipe. We're declaring a key that already exists first and a new value. So that's going to give you basically like an update. And the bottom value, or the bottom line there, is combining removing a field and adding a new field. So it's like renaming a field. Types. Everybody loves types. So everything in Elm has a type that is known statically to the compiler. But none of the examples that I showed you before actually have type annotations. Yet every single one of them is checked at compile time to be correct. And that is because Elm, like Haskell and other languages, has very good type inference. So it can tell by the flow of your program what types are expected where. So you don't actually need to put any type annotations in your code, but it's generally accepted practice that you would do that. And doing so kind of helps you in your implementation of a function. If you know what the types are going to be ahead of time, then you can kind of figure out what your code needs to do. So some examples of types. The colon there, you can read that as has type. So 5 has type number, 4.5 has type float. There are separate types for string and character. Strings are double quotes, characters are single quotes. You'll notice that all the types here are in uppercase, except for the first one, number. and that's not a typo. Number means that it can be either an integer or a floating point. It depends on how it's used and what you do with it. Keyboard.presses is an interesting one. That comes from Elm's signal library. Basically keeps track of all the keys that are being pressed over time. So signal is a value over time. If you're familiar with reactive extensions for various languages or Bacon.js, something like that, same idea. We've got types for records. The bottom two are types for functions. So a function type will list the types of the arguments that it takes, and then the final type there will be what it returns. So we've got add, which takes an integer and returns an integer. And then we've got map, which takes a function. That's what the parentheses around the A and B mean. It takes a function A to B, a list of A, and returns a list of B. The A and the B are type variables again. So anywhere you see the A, it's the same. It's always going to be the same type. And anywhere you see the B, that's always going to be the same type in that function. The interesting thing here is that A and B can actually be the same type. They don't have to be different. So in this example, you could do a map that takes an integer to an integer, and that's totally valid. They don't have to be different types. All this is saying is that they can be different types. It's not restricting it any further. All right, and this is where everything goes horribly, horribly wrong. Okay, so the code I'm going to show you is a simple counter application in Elm. The idea is not to go through every single line and take a look at what it's doing. It's just to quickly see how Elm programs are broken up, because all Elm programs are broken up into the same parts. So we've got the model. We've got some actions that operate on the model. We've got an update function, and we've got a view function. So model, update, and view, all three of those exist in every Elm application. Component, full-blown application, whatever you want to call it. So here we've got a type alias, which is just another way to refer to this record. So I've got a model that has a value and an operation count. I'm going to initialize that to both values to 0. I've got some actions that I can do. I can increment it, I can decrement it, I can reset the value, and I can reset all the values. So what I'm doing is basically up and down a counter and keeping track of how many times you've clicked a button, except for the reset all. That'll reset everything back to 0. So that's the model. Here's our update function. I've got a little helper function, stop at 0, to make sure that if I go down to 0, I don't go into negative numbers. We can kind of ignore that. So here we have an update function. It takes some action and a model, and it will give us a new model. So increment is going to update both the model value and the operation count and give us a new model. Decrement is going to check that we're not at 0 first, and then subtract and update the operation count. Reset is going to reset the value to 0. Reset all is going to just reset everything back to 0. And that's all you have to do. There's no other kind of plumbing necessary in order to react to the changes. Then we've got our view function. Now I've broken this out into a lot of little helper functions. Yeah? Question. Sure.
Is the language white space sensitive? Or?
Yes. Yeah. So it's kind of layout sensitive, I guess is how you could put it. And one of the things that Elm strives to do is to have a consistent look to all the applications when people are doing it. So there's actually an Elm style guide that says, okay, if drop one line if you have an arrow here, if you have an equal sign there, because in Elm and in Haskell and other languages like that, you can have a multitude of different styles. And the idea here is to keep them all consistent. So this stays fairly consistent to that. I might have messed up a couple places. So I'm going to go down to the bottom here to show you the whole view function. But you can see this uses the Elm HTML package, which is basically a DSL over HTML elements, HTML attributes, and HTML events. Okay? So we can create divs by calling a div function, giving it a list of HTML attributes like classes, IDs, event handlers, and then we can give it a list of child elements. So here, for example, we've got a button, it responds to on-click addresses. And in this case, this button is going to do reset all, and this button here is going to do the reset value action. This is a function that just tells us the total number of operations. And then this is our actual view function, and everything else above that was just gets used in here. So we've got a div, give it a class, page header, and then we're going to list the current value, some buttons to count up and down, some buttons to reset, and we're going to spit out the total operations count. So this address thing here, just so I'm not totally lost on it, it's basically telling Elm where to send these events. It's like, they call them mailboxes. So it's like a mailbox. You say, I want to send this action to this address. But in true Elm fashion, there's a package that abstracts all of that away. So the startup package, you simply tell it, this is my model, this is my view function, and this is my update function. And it takes care of wiring up all of the signals that need to be involved. All you have to do is provide it these three things. A view that can take an action, a model, and give it some HTML. An update function that can take an action and a model and give it a new model, and whatever your model is. Cool? So let's see if we can get it to work. Voila. So this is what it spits out. I've already compiled everything because I wasn't sure if I was going to have internet access or not. So essentially, this is what it spits out. So when we click here, we're going to get an increment action, and we're going to bump by 1. Here, we're going to do 0. We can keep clicking this. The operations count goes up. This never goes down below 0 because we guarded for that. We can reset that value. The operations goes up, and we can reset all. Pretty simple, but even more advanced Elm programs are just made up of those three things: view, update, and model. There is something called the Elm Architecture, which is, if you're familiar with the ideas of Flux and having a single blob of a single object be your entire application state, and you kind of nest your components and your data, it's the same basic idea, just forwarding on calls. So that is the demo. Any questions real quick? Yes, sir?
Let's make sure we get the mic over to anyone asking questions real quick, so we've got those on the stream.
Thank you. I have two questions. When you're building HTML elements, does it apply those directly to the DOM, or do you group those changes and apply those in batch?
So it's actually a virtual DOM system, just like, similar to like what React does. So when you are building up DOM nodes, what you're doing is you're building up a representation of what your DOM will be, and then the runtime takes care of going and making those updates. Now, when you are updating, it's going to diff the current version of the virtual DOM with the new version of the virtual DOM, and then make updates based on that diff.
Okay, and then my second question is the library that wires everything up, does it do two-way data binding by default? And is there a way to do one-way data binding? It's all
one-way data binding. Okay. There's no two-way data binding.
Oh, okay.
So you say you have a click action, and that's not bound directly to something. That just says, okay, take the existing model and this action and send it to that update function. And now I'm going to give you a new, that function is going to give you a new HTML or virtual DOM. Now diff that with the current virtual DOM and make those changes. Yeah.
Here we go.
Oh, sorry. Gotta wait.
Thank you. I have 4 or 5 questions here. You mentioned this is a compiler. So does it mean that only the object is being sent to the browser, or the source code goes along with it?
The source code goes along with it. So it takes an Elm file, and it takes your Elm file and compiles it to a JavaScript file. You source that in your HTML file, right? Like you would any normal script tag, and then there's
so
a little bit of JavaScript that you have to do to actually embed it into an element, but that's about it.
So since the JavaScript is, the browser requirements are the standard browsers. Okay. Who's behind Elm? Who created that?
Elm was created by a guy named Evan Saplicki, and I'll probably get the name wrong, but he works at Prezi full-time. It was part of his PhD thesis, or was his PhD thesis.
Was the compatibility with jQuery?
None. No, I mean, I'm sure once you have it on the page, you could mess with it if you wanted to. But the idea here is to build your entire application in Elm rather than using libraries like jQuery or things like that.
Thank you.
Sure. Okay.
All right. Thank you very much, Jesse.
Thank you.